present you it's just a science case. So, right. And so it's related to the dynamics of the venus. It doesn't. And the scientific test consists of the observation of the planetary-scale waves in the atmosphere of Venus, which are still quite poorly characterized. And some missions before are provided for Earth informations, in particular the UV images made by the photopolar emitter of the Venus, Pioneer Venus orbiter. And from several series of data, data consisting of both brightness variations and also cloud-tracked winds allowing to retrieve the oscillations of the wind, that is the zonal and the meridional wind. It has been possible to make Fourier transform to try to find for periodicities. And you may see here the results of this Fourier transform from a series of images, and are showing that exhibiting very clearly several waves, mainly two waves here, that is Rossby wave of period 5 days and retrograde wave, and an equatorial Kelvin prograde wave, which is seen both in brightness and in zonal mode. So these waves are well-known waves on the Earth, and they are due to the effect of the centrifugal force, that plays the role of Coriolis force on the Earth's atmosphere, and the pressure. It's a result of a combination of pressure and the centrifugal forces. So you may see that they are well characterized, but there is a strong variability between each epoch. For example, in 1982, there were no wave at all detected. So it is an intermittent process. Other observations from Galileo and from the Venus Express Venus monitoring camera, UV images, and you may see here Fourier transform also for both zonal and meridional winds, and you find again there's waves, and you can see that here that the red color means that the statistical significance is high. So the Rossby wave is clearly detected, you see here, and it is in fact retrograde. It may be seen by comparing this value with the frequency corresponding to the zonal periodicity, the zonal. You may see here this wave and this other one. There is a variability again, and it seems that the Kelvin wave is more present when zonal wind is weak. So it is from a GCM, that is the dynamical core of the GCM generates waves naturally. That's what we do. Waves exist. They are generated. And you can see here, this is the diagram with the frequency and the pressure, that is the altitude. With the altitude here, you may see that the GCM exhibits Kelvin waves here at just below 60 kilometers altitude. And it's interesting because in fact at 70 kilometers altitude, where Kelvin waves are seen in the figures before, that is on UV images at 70 kilometers altitude, the GCM doesn't generate Kelvin waves. So it shows that clearly the GCM general model does not properly represent the wave activity Venus, of course. And this one, it was at the equator and at higher latitudes. You may see here wave activity. So you have, to the left here, you have the thermal, diurnal and semi-diurnal tides here. The same here, and you may see that the waves here, which are in fact baroclinic and near the pole, mainly baroclinic. So another kind of structure seen in the Venus atmosphere, it has been measured recently by the Chassefière orbiter, by the long-wave infrared radiometer, is this bow-shaped structure, which is in fact a gigantic structure extending over 10,000 kilometers. And you may see here the relief that is the mountain below, the islands of Venus below the wave. That is 40 or 50 kilometers below. And the particularity of this wave is that it is fixed, more or less fixed, and with respect to the surface of Venus. And this wave doesn't move with the global general zonal circulation compared to the Kelvin and Rossby waves. And it is interpreted as the trace of gravity waves generated by the interaction between the wind and the mountains. And it's very interesting because this interaction can give an idea of the transfer of angular momentum from the surface of Venus, from the solid surface to the atmosphere. So understanding better bow-shaped weight is also interesting in this frame. And so I will come back to the scientific objectives, but so for past missions, the orbits were really not ideal, not optimal for measuring waves. Pioneer Venus and Venus Express are on high inclination orbits, and with a poor time coverage of equatorial regions, because the ideal orbit is an equatorial one. So, poor time coverage of equatorial regions, Akatsuki is on the more favorable equatorial orbits that are with a very high eccentricity, with a period of 2 weeks, not allowing a significant time longitude coverage. Even a Venus Express type orbit in the equatorial plane is the same, but in the equatorial plane it's far from being ideal, because you may see here the satellite in orbit around Venus on the Venus Express type orbit in the equatorial plane. You have limited the satellite zenith angle at 70 degrees, and the area blue shows the coverage of Venus, and because the satellite spends only a very, very small time above the hemisphere facing the ellipses, the coverage of all this hemisphere here is very weak. Of course, this hemisphere facing the ellipses is much better covered. It is not interesting orbit. There's a limited range of observed longitude and problems with day-night regular sampling and with topographic features which cannot be seen. Don't forget that Venus rotates on itself in very long time. So the day of Venus is around 70 So a circular equatorial orbit is the best configuration for monitoring the waves. But so you may see that with only one satellite, one small sat, let's say, from a circular orbit, the coverage is only partial, let's say about once. The ideal configuration is to have two satellites, or three will be better. Already two satellites, seems to be very nice. With two satellites looking at Venus and mapping Venus in several wavelengths in the UV visible, to have both brightness and zonal and meridional winds by tracking features, cloud features, at these altitudes, These two channels are very interesting to probe during the night lower level, that is 50 kilometers, both zonal and meridional winds. And that, of course, the contrasts are not as good as in the visible, but are still good enough probably to retrieve information on waves at 50 kilometers. And one thermal infrared channel, similar to the one of the Lear instrument on Akatsuki, to probe on day and night this amplitude range and to retrieve the temperature. So, thanks to the system, we have both the temperature, the brightness, and the visible, and UV, and the zonal and meridional winds at this altitude, and to some extent at this lower altitude, 50 kilometers. So the objectives are to analyze the waves, as I showed you, by Fourier transform, to get time series, and to have long series over long periods, and also to be able to track on the long term the evolution of the shapes of the UV markings, and to make a survey of stationary ball-shaped waves as measured by Akatsuki. So this configuration is good. Of course, the best one would be to have 3 satellites at 120 degrees from each other. And with 2 satellites, you see that the coverage is very good. And typically, the time coverage is 2/3. And with 3 satellites, the coverage would be total. So scientifically, it's very exciting because the Venus atmosphere is not well modeled. As you have seen, the GCM doesn't properly represent the wave activity in the Venus atmosphere. And the wave activity is crucial. Why? Because the atmosphere of Venus is in the state of superrotation. That is, the atmosphere rotates around the planet in about 4 days at 70 kilometers, whereas the planet, the solid planet, more than 100 days. And the mystery of Venus is that the rotation of the atmosphere is more or less a solid rotation. So it is very clear that the Hadley circulation transports angular momentum to the poles, but if it would be the case, in fact, the regions, the atmosphere at higher latitudes should rotate faster than at low latitude, but it is not the case. It means that there is also transport of the angular momentum from high latitude to low latitudes. And waves can transport all 3 types of waves. Organic, the planetary-scale waves can transport momentum. And to be able to understand how this momentum is transported is crucial to really validate and improve the general circulation models. So what is the nature of waves and of their variabilities at 70 and 50 kilometers? So we need long time series of the temperature, of the brightness also, and of the meridional and zonal wind. And it would be useful to have that at least over 3 Venus days, that is 1 test year. In particular, to also be able to monitor the diurnal tides, diurnal and semi-diurnal tides, which will allow to understand the angular momentum horizontal transport on the day side and less accurate on the land side. And to understand also to monitor the global circulation pattern in relation with waves over long periods. And the ball-shaped structures, in particular, to understand not only the transport of angular momentum across latitudes, but also from the surface to the atmosphere. So what are the needed instruments? So the instruments must be an imaging multispectral radiometers with so it is more or less the addition of an instrument comparable to here on Akatsuki and one comparable to the Venus monitoring camera, Venus Express. So these 2 instruments together are about 6 kilograms, but I think that today probably it is possible to do that for much less. To be studied. The field of view of these 2 instruments is typically 15 degrees. It's okay. 40,000 kilometers, the full Venus distance of the field. The spatial resolution is about 1 milliradian per pixel. It is okay, 40 kilometers, 40,000 kilometers. It's sufficient to fully analyze the waves. So the question is to know, of course, to which extent it is possible to reduce the mass of such an instrument and to integrate both into a single one, which is not easy in particular in the thermal infrared. So we have made a small calculation, it's approximately that. So let's assume that the main orbiter deploys the first small sat here. After that, the main orbiter is moved to a slightly lower orbit in order to have a differential velocity. And so progressively, on this orbit, the main satellite will be phased with respect to the first one here. And at some time, at 180 degrees, the main satellite is put again on the initial orbit, and the second one is deployed, or the second one can be also the main satellite. And it is just an approximate calculation, but it is easy to see that the required delta V for putting the two satellites at 180 degrees from each other is of the order of 100 meters per second divided by the time required to do this operation. And if the time is 1 month, it is 100 meters per second. If we can afford 2 months, it is 50 meters per second. 1 year, it is 10 meters per second. So that's what we find for the best components. So what about the proposed idea? So again, the scientific objectives are very strong. And this is a new science where the science of waves in the atmosphere. So a couple of small nadir-pointed satellites equipped with radiometer can do the job. And MPVIEW should be deployed by a larger mission inserted in an equatorial circular orbit. Perhaps a generic mission deploying several small satellites, possibly for also other purposes. And so the next step of the study, so what we can do from our side is to optimize emission parameters, in particular to use a GCM to calculate, generate waves, to add noise, to add intermittence, and to add also for the partial time longitude coverage depending on the observation configuration, and to generate Fourier transforms to see what would be the optimal position of the emission and the optimal sequence to get the most, the maximum information. So there are two other points, of course, the study of the Earth's Venus trajectory and of the Venus insertion orbit. For example, there is a work on the GPF and missions. And also the question, of course, of the instrument, which kind of instrument, what can we do for which power, for which mass, which telemetry data, and so many things to do. But so this the problem is open, and if there is any group interested in working on that, I think that we are open to collaboration. Thank you.
So, any questions? Okay, now.
Hello, thank you. I was just wondering if you have any estimate for the size of the CubeSat or the size of the payload.
No estimate. It's just a scientific point. Anything. That's just science.
Thank you.
You talked about 1 year lifetime for the science data you mentioned. So it is a very harsh environment. So what would be the overall lifetime for CubeSats there, including calibration, deployment, and then science?
So I think that after that it's very compromised to find even with 1 or 2 months operation, it will be better than the existing data. So even with a few months, but if we want to cover the whole sample of waves, we need at least 4 months. 4 months will be already good. 1 year would be ideal, and with 1 or 2 months, it's probably much better than what we done before. So there is a full study on that. To understand exactly what is possible.